Okay, let's go for the next topic. The next topic is gonna be atomic spectra. By the time of Isaac Newton, this experiment was familiar, and is the case when we have a white light passing through a prism. A rainbow was found in the other side, right? This is because of refraction. Correct. Later, by 1814, Fraunhofer repeated experiments done by Isaac Newton, but in this case, he magnified right light right passing through the prism, especially light coming from the sun, and he found that many dark lines were shown on the spectrum. These lines were called the spectral lines, but by that time, nobody knew the origin for those spectral lines. Later, by 1857, Robert Bunsen invented his burner, the Bunsen burner. Okay, this Bunsen burner was used by Kirchhoff, Gustav Kirchhoff, and he repeated the same experiment as Fraunhofer. But in this case, he used this burner that produces very clean and colorless flame. When we sprinkle some chemical element, right, the flame changes in color, and the color is unique for a specific chemical element. Using this again Bunsen burner, Kirchhoff made the same experiment, repeated the experiment similarly to Fraunhofer, and he found the spectral lines for chemical elements. So Kirchhoff created a spectroscopy. Okay, and he found three types of spectra. He found continuous spectra, that's a rainbow that is produced by solid object or liquid that are very hot. Correct. Absorption lines or dark lines again is produced by gas, which is cold and in front of a hot source. Correct. So in this case, we have absorption. We know today that in that case we have an electron that jumps from low level to high level. So we have absorption. This is a photon. Remember, photon. Correct. And we have the other type, which is line emission. In this case, we have bright line, and that happens when we have a hot gas. So it's radiating light, emitting light, correct? And we have emission. It goes from higher level to lower level. And right here, the spectral lines are in color if we are in the visible, right? Green, blue, yellow, and so on. In this case, all the lines are dark. In this case, we have bright and in color. Perfect. So we have then a quick review on the spectra. Later, the spectrum of hydrogen was found, right? And the relationship of the wavelengths of this spectrum was given by a high school teacher, Balmer, and those are called the Balmer series. So Balmer series, and this is the relationship he found. This is by 1885. He found this relationship. This is for hydrogen atom only. This is equals to the wavelength is 3.6456 times 10 to the negative 7 meters, correct? N squared, this is a constant, divided by n squared minus 2 squared, correct? Perfect. Later, this is in the visible, of course, this is for hydrogen atom in the visible. Later, another series were discovered in the ultraviolet and in the infrared. Now, to get a better pattern of the wavelengths, this relationship is used, correct, to cover all the ranges of the spectrum, right, electromagnetic spectrum. And this is again the general pattern. We have that 1 over lambda is equals to 1 over 3.6457 times 10 to the 56 actually, negative 7 meters, correct, times this is again the constant times n squared minus 2 squared divided by n squared, correct. Now let's factor out 2 squared, and this is equals one more time 1 over, it's gonna be actually 2 right here, 2 because we are factoring out 2 squared divided by 3.6456 times 10 to the negative 7 meters, correct. And now right here we have a factor of 1 over 2 squared minus 1 over n squared, correct. Or more generally, we have this pattern 1 over lambda is equals to r. Now r is this constant times 1 over m squared minus 1 over n squared. This covers all the ranges in the visible, ultraviolet, and infrared. Okay, great. And this r is called the Rydberg constant. And for hydrogen, this is the value. R is equals to 1.097 times 10 to the negative 2 per times nanometers inverse. Okay, nanometers inverse. Correct. And using this equation one more time, this one, 1 over lambda is equals to r, correct, times 1 over m squared minus 1 over n squared. We get the different series that are discovered for the range in the electromagnetic spectrum. For example, in the ultraviolet, for ultraviolet, m is equals to 1, correct? And this is called the Lyman series. And this is 1 over lambda is equals to, just substitute the value right here, r, correct? 1 over 1 minus 1 over n squared. In this case, n is 2, 3, and so on, right? N takes the values of 2, 3, and so on. Correct? Perfect. What about in the visible? In the visible, m is equals to 2, and these are called the Balmer series. And again, this is the relationship for the wavelengths, correct, for all the wavelengths in that series equals to r times 1 over 2 squared minus 1 over n squared. In this case, n is equals to 3, 4, 5, right, and so on. And finally, let's go to the infrared. M is equals to 3, and this is the patching series, correct, series, and the same thing, right? The same formula. We're changing only the value for m. 1 over, in this case, 3, right, the square minus 1 over n square. In this case, n takes the values of 4, 5, and so on. Correct? You see the same general pattern for the wavelengths at different ranges. Okay, great. Now let's go to the analysis of the spectral lines that we found before, and also creating the new matter of the atom. Okay. Okay. At the beginning, it was believed that the atom was solid. It was a single object, sphere. Correct. Later, the electron was discovered, and a new matter was created. Correct. It was believed before that the electrons were inside of this, like a cloud of positive charge, right? This is positive charge, right? And inside these are the electrons, right? Negative charges. Okay, that was created because of the discovery of the electron by J.J. Thomson. Okay, later, Rutherford found that actually this cloud of charge energy is positive energy is concentrated in a small region that he called it the nucleus. So we have another model. In this case, the positive charge is in the nucleus, right? And we have the electrons moving around that nucleus. This is by Rutherford. This is by 1900. By 1900. Correct? So, and this is called the planetary model of the atom, right? Planetary model of the atom. Okay, this model was used by Niels Bohr. Let's go to Niels Bohr. Niels Bohr. Okay, Bohr. Niels Bohr found he used these ideas from Rutherford to create or to study the spectrum, right, of hydrogen. Okay, let's do it. So Niels Bohr created this model, okay? The Bohr's model of the atom. Okay, in this case, he used the same idea as Rutherford, all right, using the planetary, right, planetary model, right, of the atom. This is coming from Rutherford. Also, but when we use this model, right, we have this positive charge and we have an electron that is moving around this nucleus. We know that every time we have a charge and the charge accelerates, correct? The charge irradiates energy. We can do it this way. The charge disappeared and we accelerate it. Right? We accelerate it, so energy is radiated. So what happens with this electron? This electron is being accelerated because it has centripetal acceleration. If this electron has centripetal acceleration, the electron radiates energy. If the electron radiates energy, right, the distance decrease, and is supposed to crash onto the nucleus, and the model disappears. The electron in the atom disappears in this way, but that doesn't happen. Means what? We need to save this one. In this case, Bohr said, well, there are allowed orbits allowed by the electrons where the electron is not radiating energy. Correct? Perfect. That's the second statement for Bohr's model of the hydrogen atom. Right? It says electrons do not irradiate energy for some orbit. For some orbits. Correct? Like in this case. Other way, if it radiates energy, well, the atom disappears. Okay, great. Another statement is that only the atom can radiate energy when it goes back and forth between two allowed orbits. For example, if the atom absorbs energy, right? The electron goes to that level, so energy is absorbed. When it's going back, right, energy is emitted. Only in these two cases we have the emission of energy as a photon, correct? So it's represented in this way. So we have that this change in energy, correct? Change in energy is equals to final minus initial energy, and is equals to plus minus the Planck's constant times the frequency, correct? And remember, this is the energy of a photon. So it's positive when it's absorbed, the electron absorb energy, negative when emit, right, that energy. Okay, perfect. We have another statement for this model, which is that angular momentum is quantized. Angular momentum, the symbol is L, is quantized. And Bohr found this angular momentum is equals to n times h. Remember, h is the Planck's constant, correct? Divided by 2 pi. N is a whole number. 1 is equals to 1, 2, 3, and so on. Okay, so this is found, of course, NRV and h over 2 pi. We have also that the change in energy is equals to plus minus this quantity. Perfect. Also, Bohr found that if the electron changes its angular momentum, we have emission of energy too. Okay, radiate energy. Correct? Perfect. Now these are the statements for Bohr model of the atom. Correct? And it's important because it worked and found exactly the same wavelength as found by Balmer in the Balmer series. Okay, great. Let's go then to energy of these orbitals. Let's go to the energies. The energies of the Bohr orbit, right? The energies of the Bohr orbit. Bohr orbits. Okay, let's do it. So what do we have? Well, we have that we have a hydrogen atom. We have only one electron and one proton. Correct? Perfect. And this is a distance or between these two charged particles. It's the same thing as we have two charged particles, right? One is positive, one is negative. What do we have? We have an attraction, an attractive force. According to Coulomb's law, right, that force is equals to what? Force is equals to a constant K, right? Q1, Q2 divided by R squared. Because we found that they have the same magnitude, correct? The same magnitude. So we can represent this in this way. It's equals to K E squared divided by R squared. This is the case when we have only one proton. What happens if we have two or more protons and only one electrons are moving around that nucleus? So we represent the numbers of protons in this way and the charge like that, correct? To have this situation right here, correct? Now this is equals to what is equals to actually K is Z, correct? E squared over R squared when we have more than one proton in the nucleus. Remember K is equals about 9 times 10 to the 9 newtons meters square, right, coulomb per coulomb square. That's correct. Let me see. Let's solve for. Yeah, it's correct. And that should be K. We know that from the previous chapters. Okay, perfect. Now we found that this is the force between two particles. Also, we know that the potential energy is equals to K times the charge divided by, actually potential is force. Remember, force times the distance. Okay, force times distance. It's gonna be the same thing as in this case. It's gonna be, for the force is that one times this, is gonna be K Z E squared divided by R. Okay, that's the electric potential energy. Now, let's calculate the torque energy of this system. The torque energy is equals to kinetic plus potential energy. Okay, let's do it. What should be kinetic? 1/2 mv squared. And what is the potential? The potential is gonna be negative, right? Negative is gonna be negative because this is positive and negative. So when we multiply, right, becomes negative. Okay, perfect. Negative what? K Z E squared divided by R. Okay, great. Now, when we have an object moving in circular path, remember the net force is equals to the centripetal force. So the force acting on these two charges, on the electron, to keep the electron moving around the positive charge is gonna be the centripetal force. And the force again must be equals to the coulombs, to this force, right? Electrostatic force, Coulomb's law. Okay, perfect. So what do we have? Centripetal force, remember, is equals to mv squared divided by R. And we found that that force is equals to the electrostatic force right here. Okay, Q, instead of Q we use E, right? The charge squared divided by R squared. So means that these two must be the same. So means that mv squared over R must be equals to K. We use Z, right? Z, in general case, Z E squared divided by R squared. Probably here we have that mv squared is equals to Kz E squared divided by R. If we divide this, because it's divided by 2, we divide this by 2, we divide this by 2. So this quantity, this one right here, is equals to that. So what do we have? This is equals to Kz E squared divided by 2R minus Kz E squared divided by R. Remember, Z is the number of protons. Okay, perfect. And from here, it's found that the total energy of this system is equals to negative Kz squared, divided by 2R. Right? That's the total energy. The total energy is equals to Kz squared divided by R of that system. Okay, perfect. Now, what else do we have? Let's divide it by 2, right? Divided by 2, divided by 2 right here. Okay, now let's go to the angular momentum. Okay, let's go to the angular momentum. Perfect, angular momentum. And see what happens. Angular momentum of the Bohr's orbit. Okay, let's do it. We define the angular momentum. The definition is equals to mvr. Of course, that's the magnitude. Perfect. So what do we have then? According to Bohr model, right? The angular momentum is quantized. We found, it's right here, right? We found that mvr must be equals to that, equals to 2h over 2 pi. N, so it's n over 2 pi. Correct? From here, we solve for v. V is equals to n h over what? 2 pi mr. Correct? mr. Because this is the angular momentum for each orbit, right? This is one orbit, another orbit, right, and another orbit, right? This is the positive charge to the nucleus. So we represent this, the velocity that represents this orbit, n, right? N, the same happens to the radius, right? We call this radius 1 because it's n equals to 1. This is radius 2 because this is n2, correct? And so on. Okay, perfect. Now, we found before the velocity, we found, I erased it, but that mv squared is equals to kz squared divided by r. Correct? We found that part. Now what happens if we multiply this v squared and apply it right here and see what happens? Let's do it. Let's do it. See from here we have that v sub n squared is equals to n squared h squared divided by 4 pi squared m squared, right, r sub n squared. Now let's plug this value right here, and what do we have? Well, we have m times n squared h squared divided by 4 pi squared m squared r sub n squared must be equals to k z e. Let's make the same r, gonna be r sub n. Okay, when we arrange this, we're gonna get that r sub n. Okay, we're supposed to get that. Let me erase some parts right here. Let me erase these two. We have that r sub n is equals to 5.29 times 10 to the negative 11 meters times n squared over z. And this is called the radii for Bohr's orbit, right? The radii for Bohr orbit, r sub n, right? Which is this equation right here times n squared over z is the radii of for orbits for Bohr's orbit. Bohr orbit, which is this one right here. Okay, perfect. Now let's substitute this value, this one. Let's substitute this value right here. Correct? Let's see. What is the next step right here? Exactly. Let's substitute that value. These are right here on this one. And it's found that the in this case we know that the radius is also quantized, right? This we can use in this way, right? The angular momentum is quantized, right? Every time we have this n, like for example when we have charges, right? Charge is equals to n times the electron, so means that the electron is the charge is quantized, right? Because the charge is a whole number of the charge of the electron. We cannot have half or 1/3 in free space, right? So it's quantized. The same thing happens right here. Angular momentum is quantized. The radius, right, is quantized. What else? Energy is also quantized. We know that also from Planck's analysis, right? Energy is quantized. Also right here, we get the same condition. In this case, for the hydrogen, this is equals to negative 13.6, correct? Electron volt times z squared over n squared. Correct? Perfect. And this is one of the most important equations in this analysis. Correct? Perfect. Now let's go to the energy level diagram, right? And using this formula, we get the energy, right, level diagram for hydrogen. Okay, for hydrogen, this is for n equals 1, for n equals 2, n equals 3, right, n equals 4, n equals 5, and so on. For n equals 1, which is the minimum energy for the electron, for the atom, we call this the ground state, right? Ground state. Right? We call this the quantum state, right? So this is the ground state. Correct? This is in equilibrium. The other states are called the excited state, right? This one are the excited state. But before that, let me give you the value. This is negative 13.6 electron volts. For n equals 2 is equals to negative 3.40 electron volts. For the next one, it's gonna be negative 1.51 electron volts. For the next one, it was 4.85 electron volts. And these are coming from here, correct? This is for the first one. When we take this to be 1, it's gonna be negative 13.6 divided by 1 square. The next one is equals to negative 13.6 divided by 2 square. The next one is equals to negative 13.6 divided by 3 square, right, and so on. We're changing n, right, in this equation. We get these values. Perfect, and so on, right? We have the next one right there. These are called excited state. Correct, excited state. And the minimum, right, energy possible is the ground state. The rest have more energy, right, than the ground state. Correct. Perfect. And we have, in this case, how we can find the change in energy. Correct. Is equals to, in this case, 13.6 times 1 over n final minus 1 over n initial. So hydrogen. Okay, also the wavelengths. How we can find the wavelengths? Well, it's gonna be 1 over lambda equals to, or now z squared times what? Times 1 over n final square minus 1 over n initial square. These formulas help us again to solve for. Now remember, it's kind of similar to this one. Look, very similar. Correct. This is for a different transition right here. But we have final and initial transitions. Okay, great. And finally, let's apply the Broglie wavelength to this analysis and find why the air momentum is quantized. Okay, let's do it. This for Niels Bohr, this model was okay. Niels Bohr, okay. Bohr, the model of Bohr, right, was by 1913. 10 years later, we have the Broglie wavelength. Okay, the Broglie, right, wavelength. Okay, lambda. And this is, in this way, lambda is equals to max Planck's constant divided by momentum is equals to Planck's constant divided by mv. Means that the electron behaves as a wave. So in this case, if the electron behaves as a wave and is in circular path, we are familiar, for example, with the standing waves that are sustained between two fixed points. The same thing happens with the electron, right? The electron has a specific distance and is moving in that distance. When we have standing waves, the waves are moving a specific distance, correct? Let's see what happens to the standing waves. When we have a standing wave, for example, string, right? This is the fundamental mode, correct? The fundamental mode. When we increase the frequency, what happens? Well, we have, right, this pattern, right, like that. If we increase the frequency, now we have 3 loops, correct? And so on. Now imagine that we have an electron fixed, moving into fixed point, like when it's moving in an orbit, right? It's only one distance, or it's only one distance, correct? So in this case, the electron is supposed to be, because moving now as a wave, is supposed to create a whole numbers of waves. Like in this case, if we have a wave starting here and goes to this point in return, it produces, right, a whole numbers of wavelengths. The same thing happens right here, right? The whole numbers of wavelengths, correct? The same thing must happen to the electron. To the electrons to be in an orbit without radiating energy must create or must be in the way that it produces a whole numbers of wavelengths, similarly to the standing waves. That's the idea. Okay, perfect. For example, this is the electron moving in this way, correct? And you're supposed to have a whole numbers of wavelengths. It cannot be, right, like maybe in this way, look like this, like that, and it doesn't complete a whole numbers of wavelengths. So this is not sustained without radiating energy. But in this case, if the electron produces kind of standing waves, can be there without radiating energy. That's the idea. Okay, perfect. Now let's continue this analysis. Okay, we have that this is the de Broglie wavelength lambda. Now we mentioned that the electron must be producing standing waves because the electron now behaves as a wave, and then means that the total path by this path must be equals to the whole numbers of wavelengths. But what is the total path? The total path is the circumference. Circumference is 2 pi r, must be equals to whole numbers of wavelengths, right? The circumference must produce a whole numbers, right, of wavelengths, like that. Perfect. That's the condition. Great. Now, in this case, what should be the okay, is equals to that. What should be the angular momentum? Also, we found that 2 pi. Okay, let's substitute this lambda from here. Look, from here, let's substitute lambda. Lambda is equals to what? It's equals to well, it's over here. It's h over mv. Let's do this. Is 2 pi r is equals to n. What is lambda? H over mv. Correct. This is n. Let's rearrange it. So what do we have? It's gonna be mvr is equals to, let's multiply, let's use cross multiply. It's gonna be n h over 2 pi. Correct? But what is this? This is the angular momentum L, right? Angular momentum L. It's gonna be over there. Okay, perfect. It's L. So L, which is equals to mv squared, must be equals also to n h over 2 pi. And from here, you see now that the Broglie wavelength is found that Niels Bohr was right? The angular momentum is quantized and is given in this way, right? L, the momentum is equals to whole numbers of h over 2 pi. Correct? Perfect. Now, with this analysis, we finished this part. In the next video is going to be the second part for atomic spectra. Okay, great. See you in the next video.